Swayam Prabha. Digital India. Educated India.
Okay, so we will talk about pseudorandom sequence. This is basically this is a neat field of in the stream cipher, which is a symmetric key primitives. So let us just recall the stream cipher. So basically in stream cipher, what we have, this is a symmetric key encryption. So Alice and Bob, they agreed with a common key k, and in stream cipher, suppose Alice, the plain text is in binary form, plain text in binary bits, 0 1 bits, say 0 1 0 1 1 0 like this. So this is a okay. So now we have this key. So what Alice will do? Alice will run a what is called random number generator. So this is a key stream generator. Key stream generator, which takes the input as the secret key, and which should able to generate the key bits 0 1 bits again. So 1 0 1 1 0 like this. So this is the key bit. So key stream in 0 1 bits, and then to get the ciphertext, what we do? We just do the bitwise XOR. So this is 1, this is 1, this is 1, this is 0, no carry, just the bitwise XOR. So like this. So this is the ciphertext string. So this is the ciphertext string. So basically this ciphertext string, so Alice will send to Bob. So if this is, if the plain text string is say x1 x2 xn, so if the plain text stream is say x1 x2 xn, if there are n bits 0 1 bit, and so one has to get the key stream generator, which should give us the key stream k1 k2 kn, and we do the bitwise XORing, and we got this y1 y2 yn. So yi is equal to xi XOR with ki. So just the bitwise XOR. So this is basically xi plus ki mod 2, and this y1 y2, this is basically ciphertext. Yn is basically ciphertext. So this is the encryption. This is what Alice is doing, is encryption. Okay, this we are talking about stream cipher, and then Bob, how Bob will decrypt it. So Bob is receiving y1 y2 this ciphertext string, and so Bob is having same key k. So Bob is also have this key stream generator. This function is public, only secret is the secret key. Key stream generator, the same key stream generator, so that if we give the same input as the initial value, it should give us the same key stream. So that k1 k2 kn, so that if we just do the bitwise XOR again, it should give us x1 x2 xn, because this yi is basically xi XOR ki. Now again with this yi, we are doing XORing with the, this is yi and ki. So y, this is Bob is doing yi XOR ki is basically xi XOR ki XOR ki. So it should give us xi. So this is the ith bit of the plain text. So this is the decryption what Bob is doing. Okay. So, now we have already seen that depending on the key stream, this xi, our security will be I mean this key stream cipher will be more secure if this is a truly random sequence. If ki is a truly random bit, then this is a basically this satisfy the Shannon notion of perfect secrecy, and which is basically one time pad. Then this stream cipher is a one time pad. Then the stream cipher is called an one time pad, which possesses the Shannon notion of perfect secrecy. So, the truly random bit means this probability of ki is 0 1 bit. So, it is either 0 or 1. So, probability are equal, probability of 0 and probability of 1 should be equal, then it is called truly random sequence. And we have seen in the earlier class, then if this satisfy, then it possesses Shannon notion of perfect secrecy. That means, given the ciphertext, that probability of given the ciphertext, probability of the plain text is same as probability of plain text. This is the Shannon notion, and if this is true for all x, all the plain text, this is called Shannon notion of perfect secrecy, all the plain text and all the ciphertext space. So, if this is satisfied, then we are not getting any information by seeing the plain text, because plain text is public, it is just sent over the public channel. So, Oscar is also having the access of the plain text. So, now if this probability is same as this probability of the plain text, that means we are not getting any advantage of knowing the ciphertext. And by assuming this is truly random bit, we have seen in the last class that we can achieve the Shannon notion of perfect secrecy. But the problem is, to get a truly random bit is not practical, because we have to follow some algorithm, deterministic algorithm, to generate these random numbers. So, that getting a truly random numbers is not practical, is not possible in practice. So, that is why we call this is a pseudo random sequence. Instead of truly random sequence, we call this sequence x1, x2, xn, because truly random sequence is not possible. We want to be a truly random sequence, but truly random sequence is not possible to generate. Sequence is not possible to generate in practice. So, it is basically impractical to generate a truly random sequence. So, that is the reason we call this sequence which we are generating from the key stream generator is called pseudo random sequence. That is why we call the sequence coming from a key stream generator is called, that is why we call the sequence coming from a key stream generator is pseudo random sequence instead of truly random sequence, pseudo random sequence. And in this sequence we want as much randomness as possible. So, we want this sequence should be close to a truly random sequence. That means, we want to have some test on this sequence which we are getting from a keystream generator, and it should satisfy those tests. So, those are all statistical tests. So, those are basically the necessary property a truly random sequence should have. So, basically we are from the keystream generator we are getting a sequence that we are telling pseudo random sequence, because it is not a truly random, it is a pseudo random. So, now a stream swapper will be a good stream swapper if this sequence is close to a truly random sequence. So, the security of the stream swapper will depend on how good this randomness is there in this sequence. So, the security of the stream swapper will depend on how good this. Can you please go to the slide? Yeah. So, this is the stream swapper. In the stream swapper, we typically have a plain text as a binary string, and we need to generate the key stream, for which we have a keystream generator. We will take an example of a keystream generator. We have seen LFSR, linear feedback sieve register, is a keystream generator. And then to get the ciphertext bit, we just XOR the plain text bit with the keystream, and we get the ciphertext. And decryption is the reverse way. We just again XOR with the keystream, and we got the ciphertext, a plain text back. Okay, so the basic strength of the stream swapper lies in how random the keystream is, because we know that keystream cannot be truly random sequence. So, now question is how random this is. So, if Ki is truly random sequence, then the cipher is called one time pad. So, that possesses the Shannon notion of perfect secrecy. However, one time pad is not possible to have in practice, this is impractical. So, this is the reason we call this sequence as truly random sequence instead of we call this sequence as pseudo random sequence instead of truly random sequence, and the keystream generator which is giving this sequence is called pseudo random sequence generator. So, the main objective of the stream swapper is to construct this keystream as random as possible. So, we have to do some randomness measurement of this sequence. Suppose we have a keystream generator and which is giving us a keystream. Say this is a keystream generator, or we can now say pseudo random sequence generator. Basically, this is a keystream generator which is taking the secret key k, and it is giving us the keystream. So, k1, k2, kn, how many keystream we need, but it has a period. We will come to that, what do you mean by period of a keystream. So, this is the, so now we want to see how good this sequence is, how good this sequence is. So, we take a period of this sequence and we do some randomness test on this sequence. So, how random this sequence is. So, we will do the randomness measurement on this sequence. So, randomness means unpredictable property of the sequence. So, our aim is to measure the randomness of a sequence generated by the deterministic method, which is called the pseudo random bit generator. And so, we need to perform some test by taking sample output of the sequence. Basically, we take a period of the sequence and then we run those tests. So, those tests are basically coming from those are the necessary property a truly random sequence should have. So, those tests are basically necessary tests, but if we say that we are, suppose we define 10 tests and our sequence is satisfying all the 10 tests, then also we cannot say that this is a truly random sequence, because there may be some other property, thousands of property a truly random sequence should have. So, these conditions are necessary conditions. So, when we say a sequence is a good random sequence, if it pass all the tests we know, but there may be other tests, there may be other property a truly random sequence should have. So, this condition are typically necessary condition, not the sufficient condition. That means, if we pass all the test, I mean all the test means whichever we have, there may be other 500 tests which we do not know yet. So, if it satisfy all the tests, then also we say okay, this is little bit of good sequence because it is satisfying all the tests known to us, but still we cannot say this is a truly random sequence because there may be thousands of other tests which we do not know. So, this is the for this test what we do, we take a sequence and we say this sequence is periodic if after n it is repeating the bits. So, this n is called period of the sequence. So, we take a sequence like so after n, so this is ki's. So, if you take this in the slide we take si. So, anyway it does not matter. So, if si plus n equal to si for all I. So, that means after n iteration, after n we have a repetition. So, that means this is a period. So, we take a period. So, n is called, this is the minimum integer n is called, minimum value of such n is called period of the sequence. Okay. Now, we take a period of a sequence and we apply the Goulomb's postulates, which are the necessary condition to a sequence to be a random sequence, truly random sequence. Those conditions are necessary conditions. So, let us talk about Goulomb's randomness property. So, it has basically 3 rules, postulates. So, first one is telling, so every period, in every period we have exactly same number of ones or 0. I mean, if they differ by only 1. So, if you take a period like so, this is Goulomb's postulates. These tests are by Goulomb's randomness test. Okay. So, what it is telling? It is telling it has three rules, 3 postulates. First one, it is telling the we take a sequence S1, S2, Sn. We take a sequence, period of a sequence, and the first it is telling that we count the number of zeros, number of ones, and they must be almost equal. If they differ, then they will be differ by 1. So, that means cardinality of number of zeros minus cardinality of number of ones must be less than equal to 1. Okay. So, that is the first postulates. So, in every period the number of 1 differ from the number of 0 by at most 1. So, this way we can see that, and if we consider the run, in every period half of the run has length 1, 1/4 of the run should have length 2, 1/8 have the run of length 3, and so on. So, this is the second condition. This is about the run of a sequence. Run means the consecutive bits. We will take an example. So, we count that how many runs are there. So, if there are 8 runs, then half of the run should be of length 1. So, that means 4 half, there are 8 runs. So, 4 runs should be of length 1, and 1/4 run should have length 2, like this. Okay. So, this is second condition or second rule about the run. We will take an example, and third rule is autocorrelation function. So, we define this function C tau, which is basically we take a xi and we take xi plus tau, and we take this relationship and we define this for tau is equal to 0 to n, and if this is a constant function, it is n, if where t is a constant, it is n, if tau is a multiple of n, if it is 0 or if it is n to n, otherwise it should be a constant. So, this is autocorrelation function. If this is a constant function, then we say the third rule of the Goulomb's is satisfying. Okay. So, now let us take an example, suppose we consider a sequence like this. Yeah, suppose our sequence is say 1 1 sorry 0 1 1 0 0 1 0 0 0 1 1 1 4 ones, yeah, 4 ones 0. So, this is a this is a period of a sequence coming from a pseudo random bit generator. It could be LFSR, we will come to know it is basically coming from a LFSR. So, now we will apply the, so this is our sequence S and length, this is of period is 16. So, n is 16, sorry, n is 15 over here. So, after that it will repeat again. So, we take a period of that sequence. Okay, now rule number 1. So, we count the number of ones, number of 0. What is the number of ones? 1 2 3 4 5 6 7. So, number of ones is 7 and what is the number of zeros? 1 2 3 4 5 6 7. So, it is basically same. So, they have the same number of, so if they differ, they will be differed by at most 1. So, if the number of, so here it is exactly same. So, it is satisfying the first rule and the second rule is telling the about the run. So, the total run is 8. Run means we just count the subsequent digits. So, this is 0. So, this is run of length 1. So, this is 1 1, this is run of length 2, again we have a run of length 2, then we have a run of length 3, we have a run of length 4 and we have a run of length 1. So, if we just count the total number of run, there are 8 runs. So, among this, so this rule is telling half of the run should be of length 1. So, that means half means 4 runs should be of length 1. So, 4 run 1 2 3 4, this is of length 1 and 1/4 of the run should be have length 2, 1/4 of 8 is basically 2. So, 2 of the run should be length 2. So, this is one length to run, this is one length to run and 1/8 of the run should be have length 3, 1/8 means only 1. So, this is the 1 like this. So, this is satisfying, this run is satisfied. So, this is the rules regarding the run is satisfied. Now, we consider rule number 3, which is basically autocorrelation function. So, if we define this correlation function tau 0, which is this formula we will be using. So, C tau is equal to this, we take a SI, then SI plus tau. So, if tau is 0, then this is basically SI twice, if tau is 1, then SI plus 1 like this. So, if you calculate this, it will give us a constant function where C0 is 15 and C tau will be minus 1 for 1 less than equal to tau less than equal to 14. Okay. So, this is the autocorrelation. So, this is a constant function. So, this Goulomb's postulate satisfy for this this sequence. Okay. Now, we will see where from this sequence is coming. So, we know the, so there may be other test, this is Goulomb test. So, there may be other test which is basically the necessary condition a truly random sequence should have. Like we may have test like we just count, here we have counted the number of zeros, number of ones. We can count the number of these bits 0 0, 0 1, 1 0, 1 1. We count their number and they must be similar. So, this is another property of a truly random sequence. So, there could be many properties of a truly random sequence. So, those are basically, and there are many statistical tests on this. So, those are basically necessary tests. So, a truly random sequence should pass this test. Yeah. So, if we have a pseudo random sequence, it should pass this test, then it will be having more randomness. Okay, now talk about how we can get this sequence. We know this LFSR we have used as a pseudo random bit generator. So, we will see how the LFSR bits are LFSR generates the this how good sequence LFSR is generating. So, we will talk about LFSR, which is basically linear feedback shift register, and so it is basically a key stream generator or pseudo random bit generator. It is basically a key stream generator. It will generate the key stream. So, that is why it is called pseudo random bit generator. Okay, and so it is basically if we just have a 4 bit LFSR, we can just have 4 register, and it has some connection. The connection could be anywhere in the, say, connection could be here, connection could be here, like this. So, this is one example. So, like this. So, this is a 4 bit LFSR. So, this is basically whatever the bits over here and here, we will just take this out, we will XOR and we will put it here as a linearly shifting. We are shifting these bits. So, this is if the k is shared key is say alpha 1, alpha 2, alpha 3, alpha 4, which is the secret key share between Alice and Bob. This is 4 bit. So, we just put these values and then we run this LFSR. So, then in the first shot this alpha 4 will be coming out, this is a bit 0 or 1 either, and this will go here. This is linear feedback shift register, this will come here, this is come here, and this bit will be basically XOR between this and this. So, this is basically alpha 1 XOR alpha 3. So, this way we continue and we will get a key stream. So, this is key stream, and this key stream is basically pseudo random bit, pseudo random sequence, and we will see the connection between LFSR and the polynomial, and if we choose a good polynomial like primitive polynomial, then it will give us a good sequence. So, it is a good pseudo random bit generator depending on the choice of the polynomial. So, those we will discuss in the next class. Thank you.